So I think it's time to start talking about the microcontroller just a little bit. I pulled up the data sheet here on the left. We are using an MSP430 G2553. And the data sheets are crammed with so much information that you're going to get lost in it, but just some things on it that we should know is, I think someplace on here it tells us how much RAM it has. It's not much. It is RISC, if that means something to you, that's reduced instruction set computing. Low power consumption, that's what MSP stands for. It powers between 1.8 and 3.6 volts. We usually do it at 3.3. We can have an external oscillator, but it has internal. Basically, the idea is that the chip inside of it can run. All you need is power, so it's 0 and 3.3 volts on 2 pins, and a pull-up resistor on the reset pin, and that's it. It does a whole bunch of other things in here that gives you an idea. It only has 512, so this tells us the RAM. G2553 is here, and it says we have 512 bytes of RAM. We have 16 kilobytes of flash. At least that's what it says for the G2553. And so that's a lot more, but that's for our program, so we really don't have that much RAM. That ends up being on a lot of my projects the limit that I hit that limit quite often. And you can find other chips that are similar. Some of these have 256 bytes of RAM, which is not much at all. And then they give us a little bit of a view, and there's actually two different packages. It's the same guts. They'll put the same insides in this. There's actually several different devices. So this one is a TSSOP package or a PDIP package. DIP package is what we have in ours, a PDIP. But there's also a 28-pin version. And all these have the exact same die or piece of silicon on the inside that's micro-wired out to these pins. It's just that they don't connect all of them in the smaller one. We have the smaller one. We have these 20 pins, and it's mirrored very directly here. These 20 pins, they pull directly out to the outside pins. If you have the newer board, the G2ET, EXP430 G2ET, it's almost exactly the same. There's a few extra pins out here that I like. They give you 5 volts and a couple other things that are really handy. But these ones, pin 1.0, 1.1, 1.2, 1.3, 1.4, 1.5, are port 1 GPIO. So that's a new concept for us. And so let me just kind of, since my handwriting is kind of all over the map sometimes, let's look at this, and what I'm going to do for us is kind of type this out. GPIO is general purpose input-output pins. We can set those as an input or an output. To control those, we use registers. And a register controls, so they're on our chip, there are 3 total ports. There's only 2 that we have access to. If you buy the other version on a different package, then you can have access to port 3, but we have lots of, first of all, there's lots of registers. And think of register as a memory location that controls something. So it's a memory location that controls a specific feature. We have 2 ports in reality. Port 1 and port 2. I can zoom this in a little bit so that I can boost up my font size. Okay, port 1 and port 2. Okay, and there are multiple registers control each port, and there are 8 pins on each port. For example, the easiest one to see here on the left is port 2 has 2.0, 2.1, 2.2, 2.3, 2.4, 2.5, and up here is 2.6 and 2.7. So those are the 8 pins on a port. Each of those is a GPIO pin, and then there's multiple registers that control each port. Okay, so what can we control on that? Well, for starters, GPIO, we need to control whether it's an input or an output. Okay? This is done with PXDIR. We can have, in our case, P1 DIR or oops, I put a space there, dir, or P2 dir. That controls and that's an 8-bit value, okay? And I'll do this on the whiteboard a little bit. So those are the two ports that are there. Those are the two ports, and those are the two things that control whether the pins are an input or an output. We also have output high or low control. That's done on PX out. So there's one for port 1, P1 out, and P2 out. And just so that you know, there's way more registers than this that control each port. And just to show you the scope of what we're going to be doing with, or what you can do with our microcontroller, I will show you one pin, or a representation of one pin. And there's lots of data in these data sheets, so don't freak out. But this is a representation of one pin, okay? This is the actual fit pin to the actual world. This can represent either 1.0 or 1.2. And then over here, all of the ports or all of the hardware that can control this pin. And this is all of the digital logic that exists in between to do what you want to do. So for example, P1 out is right there. It can control this bank, and this bank, okay? There is P1 dir someplace right here. P1 dir controls this. And so I don't expect you to understand this big figure here. What I need you to know right now is that we have two registers for one port. We're going to start with port 1, and we're going to have P1 dir and P1 out control those things. And we already started this in a previous video, but I blew by it really quickly. Each register for each port has, and there are registers that are 16-bit, but these registers are 8-bit registers. What that means for us is we need to start thinking about this as individual things. So let's switch over and look at, I'm going to see the best, but I have not figured out a good way to describe this, okay? But let's just put a line. Here is our chip. And here's the brains behind it. No, I can't draw brains, but there's a chip in there. And we have 8 pins. And it wants to be able to control to set each one of those as an output. Okay? It wants to control those. So let's say, and so we can go through each one of these, 1.0, 1.1, 1.2, 1.3, ... Okay? But before there, on all of these, there's a switch. Whether I can assert what I want to put out, there's a switch on each one of these. Okay, and that diagram that I showed you before was showing this, but it was so clustered. It had so much different stuff on there that you couldn't see it. It was hard to see. And so these switches are all controlled by P1 dir, and there's 8 of them. So P1 dir, if we looked at it, if we looked at an actual value for this register, it may say something like 0, 0, 0, 0, easy, 0, 0, 0, 0. 8 bits, okay? That means all of these switches are open, and we can't assert anything from the brain. We can try to assert something from the brain, but it's going to stop here because that switch is not closed. Okay? It's like the door's closed, we can't get it out. And so we want to open these doors. And so if we want to put stuff out on port 1.0, and I'm sorry, I did this backwards. Here, let me rewrite this so that this is 1.0, 1.1, 1.2. If we want to assert this, we have to make this guy a 1. Okay? And so what will happen is if we make that a 1, that makes this switch closed. And then whatever the value for P1 out is,
Let's start it out at zeros as well. We'll insert through there. So if we looked at this pin right now, I can't draw the eye, but here's the eye. If we looked at this pin right now, looked at it with the DMM, it would say 0 volts. Okay? There would be nothing there. Okay. But it's still connected to the brain, but the brain wants you to see 0 volts. Our microcontroller is telling you to see 0 volts. Now, let's change this to 1. If we change that value to 1, then as we look at that pin, what's going to end up happening is we're going to be able to see, we're going to see now 3.3 volts. In our case, we have that hooked up to an LED, and so it turns on an LED. So that's the big change that you can see right there when we do that. And so each bit controls each pin on this. P1 DIR controls whether we can shove data out. Otherwise, what happens is this brain can also go and look. So there's a pathway that comes this way, and it reads what the value of the actual physical pin is back to the brain. But it's only one way. It can't assert, it can only look. And so it can look, and we can look, and so this is how we transfer data. We have to make sure that we have to know whether we want our pins to be inputs or outputs, okay? And we also want to know what values we want to put out or read what values come in. Right now, we are going to only be setting output values. And so in this particular case, that's what we've done. We've hooked up an LED, and we've turned it on. Now I'm going to bring out our microcontroller here and put it in front of you. We have the two LEDs, and you're not going to be able to see it really well because we've got a blurry image, it's far away, and we've got a crappy camera, and the LEDs are too bright. There's all multiplicity of problems. We have our microcontroller sitting out here. Pin 1.0 is wired over here to that. And so what I'm going to do is I'm going to shrink this dude down. Oops. I'm going to go back to the code, and we're going to try to understand what we did before. And let me switch this up. And I'm just going to make this equal to 0, 1. I'm going to make this equal to 0. And I'm going to comment out this code. I'm using control / does a comment. So two ways to do comments. One is this method, where you use a / star and then a * / for the n. And then we also have this. So what's going to happen now, we're going to run this code. This is making pin 1.0. Kind of weird because 1.0, going back to our thing over here, that's this right here. We're going to translate this into hexadecimal, 0x01. What the 0th bit, the least significant bit, is represented by 1, which is kind of strange, but it's true. I'll have to do this with a couple other things. And this should just turn off the LED. Yes, we want to continue. And you can see, and the LED isn't on now, and so this is going to be rather boring code. We're going to run it, almost there. Nothing happens. Okay. We did this the other day, but we're going to reiterate. We're going to run the code. Here it goes. And finally, we're going to play. And it turned the LED on. I think you saw that it turned the LED on. If I forgot to turn on the switch, in other words, that was that, it was 0, I could do this, and this LED should turn off now because there's nothing driving that LED. So hold on, ready, set, play, and the LED doesn't turn on. Okay? And so what we'll do now, the other LED, if we come back to this image that's behind my thing over here, there's two LEDs. One is hooked up to 1.6. So let's go to the videotape. So that means P1 DIR. We want 1.6. That's this one here. And so we don't want 0x01 anymore. we want 0x 4, 1. Okay? So that's what's going to do this, and I have this still here, so when we first turn this on, it's still not going to turn on the other LED. In that case, I forget which one is the red and green, but we're going to run this code, going to press the green bug button that compiles and loads the code onto our microcontroller. By the way, and I can do a shorthand, I'm going to press F8. And you can see a little arrow down here as well. His arrow is where we're at in the code, so it starts off stopped. I press 8. The one LED turns on, the other one doesn't. Okay? We can prove it the other way. We can do 4, 0, and that's going to turn on the other LED, but leaves the other one off. So right now, the red LED is on. It just turned off because we're compiling. But now the green LED should turn on. And I know you can't quite see it, but I'm going to describe it for you as if you're Helen Keller. Okay, so now the green LED is on and the red LED is off. They're both of them can be talked to from the microcontroller. We can shove data out on them. And one thing that you might want to do is you can press pause, okay? And it just, the arrow is here, which means our code is right at that point. We can look at registers. And if we look at, port 1 and 2, and we scroll down, we can look at P1 DIR, what the individual bits are for P1 DIR, and P1 out, okay? And you can look at all the other registers. Look, there's P1 in. That's that passive one that we can read in from the microcontroller. Down here is P1 IFG. What does that do? P1 IES, P1 IE, P1 SEL. Look at all of these registers. P1 REN. Look at all of these registers that control what goes on inside our microcontroller. It's for each port. It's a significant amount of information that we have to use to control pins. But right now we're only worried about P1 DIR and P1 out. Okay? And so here's a question. Does it hurt us to make all of our pins outputs? Nope, doesn't hurt us at all. I don't have any of those pins hooked up. If I had the other pins hooked up to something, I might be cautious because I don't want to have fighting levels from somebody trying to send me data and me trying to send data. That's called, there's a line level conflict. But I could make those both FF, and I'm going to go back to the code that I had before. I'm going to uncomment this. Uncomment is the same as comment, which is control /. And what this does, this line right here, is doing P1 out equals 0x01. It is setting all bits, or setting and clearing all bits simultaneously. This line down here sets and clears all bits simultaneously. And then this in between is a wait. We need a physical wait to do this. So let's play around with this just a little bit. You can see on the code, this should do what's called railroad lights. Okay? So we're going to do some railroad lights with this. And you should see the red, green swapping back and forth, and that sure is what's going on there. I don't want you to, I mean, you can't see it very well, and even if I brought this closer, I guess you can see it pretty well when I do that. So I can bring it up. I need to find a platform where I can just put this right up at that level. That might be a 3D print project or something, to where I can mount this up there if I really want to. But there's our red and green. It's going to swap back and forth. Okay, what else can we do? And that was with the 0xFF. Well, I'm going to do a little bit of, let's see what happens. I'm going to bring this down to 1FFF. This is a delay. So everything happening right now is happening in real time. And I want you to kind of predict in your mind what's going to happen as I make that change. And I have a guess that one of the LEDs is going to be on for a shorter period of time. So we're going to do railroad lights, but it's going to be a blink, a blink, a blink. Okay? Those of you who do music, it's like we have a quarter note and then a whole note. Okay? Ba-dump. Just like I said. Ba-dump, ba-dump, ba-dump. Okay? The red one is just flashing for a lot shorter period of time. 1FFF rather than FFFF. That's a big difference. I also want to point out another thing here. Maybe, I may be wrong, but if I get rid of volatile, is what I just did there, okay, I think what's going to happen is something
horrible. And I don't know, they may have made the compilers better since I first did this. I made an error. Let's see what it says. Ooh, sun sign. Okay, I put an extra S in there. And so the compiler is really nice. It will show you the syntax errors very nicely. Press play. And it looks like it's actually going faster, right? And I'm not exactly sure what's going on, but if we press pause, we can look at countdown. Countdown is actually giving us a value. It's still an unsigned int. There's a reason why we have it unsigned, but volatile, in some cases, and maybe I should pull up that example code. I'll pull up the example code that comes. So online, I've posted all the example code that we have. Okay, and if I look at the very first example code that we have, it's just a blinking LED, and I'm going to pull up their code. I'm going to comment out mine. And of course, it's opening up in Visual Studio, which is slow. I'm just going to pull up what they have for code. They do their delay just a little bit different than mine. And you could also make a new project if you want to. Here, I'll go make a new project. I'll show you how you do that. So I'm going to switch back to editing mode. I could go do a project, new, etc. But it's going to be so much easier just to do a copy and a paste. It's going to ask me first code 2, blink example is what I'm going to call this one. It's going to make a new project here. I'm going to open up the main.c. The black one is the one that's selected. It's the one that's going to compile. Okay? And so blink example is the one I want, the main.c, and we'll just do that there. I can just delete the stuff that I had before. I copied it, so life is good. They're doing a little bit different. They're doing a do while loop, and they did call this volatile, and so I'll show you what the original code does. And you can see on the LED down there, it should just be the red LED, and there's a few goofy things that they're doing that you're going to say are problems. So, oh, and I forgot something really important. Include MSP430.h. I've cut that off for some reason. Okay. Get rid of that. Recompile. Okay. And so let's look at what they did. They do a few weird things. Or equals, they did the for instead of a while. But let's just look and see, and sure enough, there's a blink here. But they also have this caret looking thing here. We have to figure out what it is. They say I is equal to 5,000. They just give it a decimal value. They say do I minus minus while. But this is what I really want to show you, is this. It's the difference between volatile and non-volatile. So volatile was there. And now it's not there. And we're going to run the code. And the LED doesn't look like it's blinking anymore. And so if I pause, oops, I did not mean to stop. Let's recompile code. I pressed F8, I'm going to press pause. You can Alt F8 will give you pause. And here's the deal, if I try to mouse over I, it says unsigned I, but it doesn't give me a value like before. And funny enough, if I put a breakpoint here, breakpoints are kind of nice, I just double click on the number, and there's no waiting in between. The compiler thinks it's smarter than you. It looks at this code and it says, that does nothing. And because we don't have the volatile tells the compiler we care about this variable. And because that volatile did nothing, the I does nothing compared to what the compiler thinks. It thinks it's smarter than you, and it doesn't compile that code. It wants to be efficient. It wants to make things more efficient. That's what compilers do. So if we put that volatile back in, we have to recompile the code now, and it's going to make it blink. Okay? So it was blinking before, but there was no delay. So you have to think in terms of real time. So this one, when I click it, there's a delay. I know it doesn't seem like much of a difference, but it is, and especially here when we run it real time. You can see the LED over there blinking. All right, we've got a couple more things that are super important that we need to cover. Let me bring over a word. Word, y'all. Okay. Okay. Bitwise operators. Okay? We have a problem with bitwise operators. If we go back to the way the code was, and we look at it, let me copy this line out. And let's do, I'll just copy the weird ones into the bigger, in case you can't see it very well. Control-Shift-V, no, it doesn't let me do that. There. Okay, P1 dir, there's an or, there's an equals, and so we got there's some interesting stuff. I think we have to go to the, no, we'll keep it right here. Okay? There's also Boolean, we have bitwise operators and Boolean operators. That's a big enough subject, I'm going to put it on a different video. We're going to go with this one for right now, and you'll have to check out the next video for bitwise versus Boolean operators, and bitwise operations. I mean, it's gonna take a little bit to get through this, so we'll do that for the next video.